Effect of interplanetary gas on a spacecraft. A spacecraft in the shape of a cube of edge length L moves through outer space with a velocity v parallel to one of its edges. The surrounding gas consists of molecules of mass m at a temperature T, the number n of molecules per unit volume being very small, so that the mean free path of the molecules is much larger than L. Assuming that collisions of the molecules with the spacecraft are elastic, estimate the mean retarding force exerted on the spacecraft by its collisions with the interplanetary gas. The mean retarding force exerted on the spacecraft by its collisions with the interplanetary gas. Assume that v is small compared to the mean speed of the gas molecules and ignore the distribution of velocities of these molecules. If the mass of the spacecraft is capital M and it is not subject to external forces, after approximately how long a time will the velocity of the spacecraft be reduced to half its original value? So, due to collisions with the interplanetary gas, the velocity of the spacecraft will be reduced. If it is not subject to external forces, after approximately how long a time will the velocity will be reduced in half. Okay, so we have the molecular flux, J is equal to 1 over 6 nv bar, number density times the mean velocity per molecule. The number of molecules hitting the front side and the back side can be calculated. Now we have a cubic spacecraft. It is moving with velocity v, and then there are molecules coming and hitting from the front and from the back. So these molecules are all traveling with their mean speed v bar because we are neglecting the distribution of velocities of these molecules. So what is the number of molecules hitting the spacecraft from the front? Well, we have the molecular flux 1 over 6 nv bar. So the number of molecules, number density of molecules in the interplanetary gas, and divided by 6. Now I ask myself, what is the speed of these molecules according to the observer in the cube? Well, the cube itself is moving with velocity v, and the molecules are coming and hitting with velocity mean speed v bar. So using Galilean transformation, I can see that the velocities of the molecules hitting from the front side is relative to the cube v bar plus v. So it's going to be v bar plus v. That's the speed with which they are approaching. And if we want to calculate the number, then it's this is the number hitting the area L square. So we have the number per time. Flux is the number per area per time. So multiply it by the area and multiply it by the time interval delta t, we find the total number of molecules hitting the front edge of the cube at time interval delta t. Now with the similar reasoning, because these molecules are approaching from the back and their relative speed with respect to the back side will be now v minus v bar. So we will have the number hitting from the back will be n over 6 L square v bar minus v multiplied by delta t. So the speed of the molecules is v bar, but because the spacecraft is already moving with v, it is reduced to v bar minus v. That's the number of molecules hitting from the back for an observer in the cube. All right. So this v bar plus or minus v is the mean speed of molecules relative to the spacecraft. Now I want to calculate the change in the linear momentum of the gas molecules, delta P gas. It is Now, for ones that are hitting from the front, and because this is elastic collision, they're reflecting with the same speed v bar. mv bar is their final, after hitting here, mv bar is their final linear momentum. Initial linear momentum is minus mv bar, so minus mv bar, p final minus p initial times the number and front will give me the change in the linear momentum of the gas molecules hitting from the front. And for the ones that are hitting from the backside, they have an initial linear momentum mv bar, final linear momentum minus mv bar due to reflection. So this will be minus mv bar p initial multiplied by the number hitting from the backside. So this will give me 2 mv bar, the number hitting from the front minus the number hitting from the backside. So here m is the mass of one molecule. Now, because we have elastic collisions and there are no external forces acting on the system, the change in the linear momentum of the cube plus the change in linear momentum of the gas, the change in linear momentum of the total system should be equal to 0, conservation of linear momentum due to having no external forces. So I can see that the delta P of the cube will then be minus the delta P of the gas, which is minus 2 mv bar, the number hitting from the front minus the number hitting from the backside. Okay, so if I substitute this for the change in the linear momentum of the cube, this is minus 2 mv bar n over 6 delta t multiplied with L square. Now for the number hitting from the front, I had V bar plus V factor. Here I have V bar minus V factor. So V bars will cancel and I will find minus 2/3, 2 over 3, mv bar and delta t L square multiplied by V, the speed of the spacecraft. Now the force exerted on the cube, the retarding force, is delta P divided by delta T. F equals ma, it's dp dt. So if I divide this by delta T, I find minus 2 over 3 m v bar V n L squared, and this is equal to m dv dt. So that is the retarding force acting on this cube that is trying to reduce its speed. So using this equation of motion, this is equal to m dv dt, integrating it from time t0 to t minus 2/3 m divided by capital M, the mass of the spacecraft, V bar and L square dt prime is integral from V0 to V dV prime divided by V prime. So here you can see this V goes downstairs here in order to form this integration. So I isolate the two variables, time and the speed variables. And this integration gives me minus 2 over 3 mass of one molecule divided by the mass of the spacecraft, mean speed of the molecules, and number density L square t minus t0 is natural logarithm of v divided by v0. So let's have t0 is equal to 0 seconds. So that's when we start the time. Then we can see that v of t will be v0 exponential minus 2/3 m divided by capital M, and v bar L square times t. And at t is equal to t prime, I will have the speed reduced to half of its original value. That's the question. So here I will have v0 exponential minus 2/3 m divided by capital M, and v bar L square at time t prime is equal to v0 divided by 2, so v0s will cancel. So I will have minus 2/3 m divided by capital M, and v bar L square t prime is equal to minus natural logarithm of 2. If I take the natural logarithm of both sides, these minus signs will cancel, and I will find the time t prime to be 3 natural logarithm 2 capital M divided by 2m v bar and capital L square. So that will be the final answer. Okay, so in this problem we have a spacecraft which is in the form of a cube that is moving through outer space with a velocity v parallel to one of its edges. So that, as you can see here, the surrounding gas consists of molecules at temperature T with number density n. That is very small, so that the mean free path of the molecules is much larger than L. So the molecules do not collide with each other. On average, instead they collide with the spacecraft. So that's what this condition ensures. So those collisions with the spacecraft are elastic, so we want to estimate the mean retarding force. Now, using our random motion of molecules, we have a molecular flux 1/6 nv bar normally, but for the number of molecules hitting the spacecraft from the front side, we will have a relative speed of the molecules being not v bar but v bar plus v, because this is already moving towards the molecules. So we will have n/6 v bar plus v, the molecular flux, multiplied by the area L square, multiplied by delta t, giving us the number hitting from the front. And those molecules hitting from the back are normally coming with speed v bar, but because this is already going away from the molecules with the speed v, it is v bar minus v. That is the relative speed of the molecules with respect to the spacecraft that are hitting from the backside. So this gives us the number hitting from the back. Now, the change in the linear momentum of the gas molecules, for those hitting from the front side, they have a gas molecule hitting from the front will have mv bar due to reflection as the final linear momentum, and minus mv bar as the initial, mv bar minus mv bar. And for the back side, I will have final linear momentum minus mv bar, initial mv bar. So minus mv bar minus initial mv bar. So this multiplied with the number hitting from front and number hitting from back respectively gives me 2 mv bar in the change in the linear momentum of the gas molecules multiplied by the difference in the number hitting from front and back side. Now, because I have elastic collisions and there are no external forces acting on the system, so basically it is not subject to external forces, then I have linear momentum conservation. So delta p cube plus delta p gas is 0. So delta p cube is minus 2 mv bar and delta t L square v when I substitute my result for n front and n back. The retarding force is delta p over delta t, which is what we were supposed to find initially. Now, solving the equation of motion ma equals the retarding force, I find velocity as a function of time, and when I look for the time when velocity is v0 over 2, I can substitute this into the time dependence of the velocity to get the time I have to wait. 3 log 2m divided, capital M, divided by 2mv bar and L square is the final answer.